Hello and welcome to this lecture in the course for Secure Systems Engineering. So, in the last two lectures, we had actually looked at how one particular vulnerability in the stack can be exploited by the attacker. In the earlier lecture, we had looked at the Return-to-Libc attack, where the attacker overflows a buffer present in the stack and replaces the return address with one specific function in the libc library. Then, in the last lecture, we had looked at a more advanced form of attack, where the attacker is not restricted to functions in the libc, but could create a payload which executes almost any arbitrary instructions. And the way the attacker does this is by a concept of ROP programs or return oriented programs. So, these attacks are some of the most advanced attacks on programs. In this particular lecture, we will be looking at a concept known as ASLR or Address Space Layout Randomization in order to prevent such ROP and Return-to-Libc attacks. So, in order to understand the impact of ASLR, we would look at these attacks from the attacker's perspective. So, the attacker's plan is as follows. The attacker, let us say, wants to create an exploit for a particular application. Let us say the application here could be the operating system, and say for example the application here for example could be the operating system kernel. So, the first thing, as we know, the attacker should be doing is to find a vulnerability in the operating system kernel. The way he would do this is by looking at the source code or by noticing something in the patches that get applied to the operating system kernel and find out that there is a vulnerability in one of these patches, or the patches actually fix a specific vulnerability, or the third way is by following the CVE. So, once he has found a particular vulnerability in the source code, the next thing is to use this vulnerability to subvert the execution. The next part is to use this vulnerability to inject some malicious code into that particular application. For example, if the application happens to be the operating system kernel, the malicious code for instance could obtain a shell which has root privileges. Now, as we know, if the attacker obtains a shell with root privileges, then he gets complete control of the entire system. Now, from the last three attacks that we have studied in this course, what we do understand is that the payloads that the attacker writes is highly dependent on the addresses. For example, in the ROP attack, the attacker would need to know the exact addresses where these gadgets are present in the libc library. So, for example, over here in this case, the attacker would need to know where the address of gadget 1, gadget 2, gadget 3 and gadget 4 are present in the library. His assumption, the attacker's assumption is that if he is able to find these gadgets in a particular system, so the attacker's assumption is that if he is able to find these gadgets in a particular system, then that attack would be successful. Now, the address space layout randomization or the ASLR works so as to make it difficult for the attacker to find such gadgets. What the ASLR achieves is that it randomizes the address space of an application, thereby making it difficult for the attacker to get specific addresses. So, for example, in this figure as we see over here, which shows the memory layout for 3 different instances of the same application. So, what we see over here is that the memory layout changes every time you run the application. Let us take, for example, one particular library over here, which is known as the ADVAP123. So, this is present at a particular location during the first run of the application. During the second run, the ADVAP123 is present at another location, and in the third run, a third location, and so on. So, since these locations are changing in every run of the application, it would be difficult for the attacker to identify the exact location where the gadgets are going to be present, thereby preventing the ROP attacks from executing. So, the ASLR is not a new concept. It was initiated by the Linux PAX project in 2001, and since 2012 or 2013, it's becoming quite common and added by default in the operating system. Both Windows and Linux operating systems now support ASLR by default. In the Linux operating systems, ASLR would randomize the locations of libraries, the location of the heap, the stack, and so on with each run of the application. So, in your current Linux systems, especially in Ubuntu systems, you can look at this particular file. You can cat this file /proc/sys/kernel/randomize_vas_space to determine whether your operating system has ASLR enabled or not. So, this particular file would have three values, 0, 1 or 2. 0 means that ASLR is disabled in that particular system, while 2 has the highest level of randomization, where 2 is the highest level of randomization. With the value of 1, what is achieved is that the positions of the stack is randomized. Similarly, the positions of the VDSO, shared memory regions, and so on are randomized. With the value of 2, what it means is that it achieves all the randomization that is achieved with 1, as well as the data segment locations are also randomized. So, this 2 now is the default setting in most Linux systems. So, let us look at ASLR in action. So, what you can do is you could run a particular program, find out that PID of that program, and as we have done before, look at the memory space of that particular program by this particular command cat/proc, the PID value of that particular process /maps, and you would get the memory map. Now, if you run that same program again, obviously you would get a different PID, and if you look at the maps for that new process, you would see that there is a change in the address map, and this change is occurring due to ASLR. Let us take, for example, the library, the libc library. So, in the first run, the libc library is present at this location B75DB000, while in the second run, the same libc library is present at B75DE000. Thus, we see that with each run of the memory address, thus we see with each run of the application, the virtual address map for that application is changing. Now, since the virtual address map changes, the locations of the gadget would change. Therefore, the ROPs based attack which the attacker has created will not work all the time. So, for your Linux box, you can actually change the value of the ASLR by editing this particular file /etc/sysctl.conf. In this, if you actually add these lines like kernel.randomize_va_space and specify a value of 0, 1 or 2, the support for ASLR can be modified for your particular system. So, we will now look at the internals of ASLR. In order to understand this, we will need to know how libraries are made relocatable. Essentially, there are two ways to achieve this. One is known as the load time relocatable, and the other one is known as the PIE or PIC, which stands for position independent executable and position independent code respectively. In the load time relocatable, the main functionality rests with the loader, where when the library gets loaded, the loader would parse through the library and adjust each address properly so that the library executes in the right expected manner. In the PIC technique, relative addressing is extensively used to achieve the same purpose. So, we will look at both the load time relocatable as well as the PIC executables in more detail. So, let us start with load time relocatable, and let us say that we want to create a library like this. So, this is the library we create. It comprises of one global variable called mylib_int, and it has two functions, set mylib_int, which essentially takes a parameter x and sets our global variable to that particular value, and the second function, get mylib_int, returns the current value of that global data mylib_int. So, now you can compile this library by using GCC as shown over here. Now, by default, at least in my compiler, in this compiler by default, compiling it with this particular syntax would create a load time relocatable code. Now, this particular code can be also obtained from this link in the directory source.relocgot. To understand how load time relocatable code works, we disassemble this library using objdump, and we just evaluate one of these functions, which is the set mylib_int. So, as we see over here, these are the instructions for set mylib_int, and the first two instructions creates the stack frame for that particular function. The third instruction, this one here, moves the contents of x, that is present in this location EBP plus 8, which essentially is the contents which essentially is the argument to this particular function. So, the argument x is moved to the EAX register, and then the contents of x should be stored into the global mylib_int. In order to do this, we have this move instruction where EAX register is moved to 0x0. So, this 0x0 is something what the compiler has put in, because this library is a load time relocatable library. Next, we see what happens when we actually execute a program that uses this particular library. So, what we do is that we create a program, link it to this particular library, and then use GDB on that program. Notice that the actual address of mylib_int is not filled in over here. In fact, it is just left as a 0x0. So, what is expected is that when this library gets loaded, the loader would parse through each of these functions, and wherever there is 0x0, it would replace that with the actual address of mylib_int. So, in order to achieve this, there is a special section in the library which will permit the loader to determine which locations in the object file need to be modified at the load time. So, this particular section is known as the relocatable table. So, we can obtain this section by using this command readelf -r lib mylib.so, that is the library that we have created. So, notice that we have several entries over here, but two interesting entries for us is the first and second. So, each of these entries determines the exact location in the library code where the loader would need to modify. Notice that mylib_int is used in exactly two locations. One is at this at this point over here in function set mylib_int, and the second one is at this location get mylib_int. Each of these locations have an entry in this particular table. So, notice that the locations which we need to modify is at an offset 473 and 47D in the object file. So, you could see that the location 473 corresponds to this 0x0. So, note that this is at an offset 472, that is A3 is at an offset 472, and 473 corresponds to this particular zeros. Another thing to note is the type. So, each of these types is of 32-bit. Thus, at the time when this particular library gets loaded, the loader would look into this table and parse through each row in this table. It would go to this location 473, which corresponds to this 0x0. It would determine that here there is a 32-bit value that is required, and this value corresponds to the mylib_int, and therefore it would obtain the correct address for mylib_int and replace the 0x0 with the actual address of mylib_int. So, in order to check whether the loader is actually doing its job, what we can do is we can write a small program which is linked, which we link to this particular library. Then we compile that program and use GDB to debug that particular program as follows. So, what we do is we set a breakpoint in main, and then when the breakpoint is hit, we do a disassemble set mylib_int in GDB. So, notice the difference between this assembly code and this assembly code. So, this assembly code is what the compiler gives out after compilation of the library, while this assembly code is what is obtained at runtime after the loader has inserted the library into the address space. Note the same instructions over here. You have push EBP, move, stack pointer, base pointer, and so on. The same instructions are present over here, but also notice that the 0x0 which is present in this instruction is replaced with this address B7FTFIF8, which is the actual address for mylib_int. So, notice that the loader has actually done its job. It has replaced 0 in this location with the actual address of mylib_int. Similarly, you could also check that the mylib_int in this get mylib_int is also replaced to point to the correct address of mylib_int. So, the limitations for the load time relocatable technique is that it has extremely slow load time, since essentially we have the loader which passes through each and every location which needs to be modified and fills and replaces the zeros in that location with the actual address. Secondly, it requires a writable code segment, which could essentially pose problems. The third limitation of load time relocatable technique is that it prevents sharing of executable code. We will not go into details about this, but in operating systems there is a process called copy on write, where typically library codes are all shared between all processes in the system. A third limitation of the load time relocatable code is that each program should have its own customized copy of the library. So, this is not what we want in practice. In practice, typically to prevent duplication, all programs that are running in a machine would use the same copy of the shared library. For example, libc, all programs that run in the system would use the same copy of libc so as not to duplicate libc in the RAM. However, with load time relocatable, since each program needs a very customized version of the library, therefore, such kind of sharing would not be possible. A lot of the disadvantages of the load time relocatable technique are removed by using PIC or Programmable Independent Code technique. So, with this particular technique, libraries can be made relocatable in the virtual address space of the process. So, essentially what is done here is that a lot of relative addressing is used. Additionally, instead of relying on the loader to actually change each and every address in the code, a special table known as global offset table or GOT table is used. So, we will see how this PIC works and how the GOT table is used to resolve the actual address of a variable. So, let us say that we have an instruction like this, where we want to move the address of a variable to this register EDX. Now, typically without GOT, we would require to know the actual address of this particular variable, and therefore, this particular instruction would result in non-relocatable code. If you have a global offset table, however, the same single instruction gets converted to 3 instructions as follows. First, we load the address of the GOT table into this register called EBX. Then we load an offset in the table, more precisely an offset of 16 bytes in the table into this register EDX. Then we load an offset into the table, more precisely an offset of 16 bytes into this register EDX. Now, at this location EBX plus 16 bytes, what is present is the actual address of this particular variable. Next, what we do is load the contents of this EDX register into this particular register. Thus, we see that instead of directly loading instead of directly loading the address of the variable into the EDX register, which is making the code non-relocatable, instead we use the GOT table. The GOT table contains the actual addresses where the variables are present, and therefore we load the contents of the GOT table and access the actual variable indirectly using the contents of the EDX. So, we will take our library that we have created and see how the compiler generates code for using this GOT table. So, the code that we will take is as before, comprising of our two library functions setmylib_int and getmylib_int, and more importantly at this particular time is this particular global variable mylib_int. So, we have seen what happens in the load time relocatable code. Now, with PIC the code looks much different for setmylib_int. So, what we see is that additionally there is a call to some function called i686 get pc thunk, and additionally there are certain other changes as well. So, let us look at more details. So, first we see the call instruction, which essentially is a call to this particular function over here, which stores the contents of the stack pointer into the ECX register and then returns. So, what we see over here is the contents of this ECX register will have the address of this particular instruction. Now, we add 1180 to the contents of this ECX register. So, this 1180 is the offset for the GOT table. So, ECX plus 1180 is an offset to the GOT table. Further, we subtract 8 bytes from ECX, which is an offset in the GOT table which contains the actual address of mylib_int. So, this actual address of mylib_int is moved into the EAX register. Third, we note that we are storing the contents of the EDX register into the location pointed to by the EAX register. So, note that the EAX register contains the pointer to the correct address of mylib_int. Therefore, the store instruction would store the contents of the EDX register to the correct location of mylib_int. So, the advantages of using PIC technique, that is with using the GOT, is that you have reduced the load time considerably. Unlike the previous case where the loader goes and changes each and every location where the global data is used, here we are using a single GOT table which stores the correct address for the global data. Thus, the overheads while loading the library is reduced considerably. Furthermore, since we are not changing the executable code, we do not require that the code segments are writable. This is quite unlike the load time relocatable technique where you actually require the code segment to be writable. Further, since we do not require customized libraries for each program, we can actually share the libraries between various programs in the system. All of these advantages are achieved because of the GOT table. Now, the GOT table is present in the data segment, and as we know, the data segment is writable. Therefore, at load time, all that the loader needs to do is go and fill in the GOT table. The drawback of this particular scheme is that now the runtime overheads have increased. Instead of directly going and accessing a particular variable, now we need to find out the actual variable from the GOT table and then make an indirect access to that particular variable, thus resulting in increased runtime. Let us look at an example of working with GOT. Let us take this small example where we have a my global data initialized to 32, and in the main program we increment the global data by 5 and return that value. Now, in order that the compiler generates a GOT table, we need to specify additional option at compile time, which is -shared -fpic. The assembly code for this particular program looks something like this. It has got a data section over here, which is my global, and it has got this code segment over here which is under this my text. So note that the compiler has created these additional functions, the get pc underscore thunk.cx, which essentially loads the address of the next instruction into the ECX. More details, we see that this particular instruction adds the offset of the GOT table to the ECX register. Then we load the absolute address of my global variable from the GOT table into the EX register. And finally, we make an indirect load of the my global data to the EX register. So after these 4 instructions, we have finally been able to load the contents of the EX register. The disassembly of this particular code looks something like this. So we see that there is a data segment comprising of this global data, my globe, and the code segment starts from this particular section, which is denoted as the text section. As we see over here, these are the important instructions which we have to analyze. So first instruction we see is that there is a call to this get underscore pc underscore thunk. What this call does is that it jumps to this particular function over here, loads the contents of the stack pointer into this ECX register. Thus, the ECX register contains the address of this particular instruction, the addl instruction. In this instruction, what we do is add the offset of the GOT table, the global offset table, to this ECX register. So now the ECX register has the contents of the GOT table. Now we take an offset in the GOT table, add that to ECX and load the contents into EX register. So now EX register has the correct address of my globe, the global address. Now we load the contents of that global data into EX register. Thus, at the end of this instruction, the EX register has the contents of my globe, which is 32. We add 5 to this contents and return this particular data. If we use readelf to determine the various sections of the a.out file that we have just compiled, we see that the 19th section has the GOT table. So this is at an offset of 584 bytes and has an address of 1584 from the start. Further, we can then look at the relocatable data and see the offset of this global data my globe in the GOT table. So now that we know how a library can be made relocatable, either using the PIC technique or by load time relocatable, we will now see how ASLR works. So in order to understand this, we have to look at snippets of the operating system. Essentially what is happening is that when the operating system invokes this function load elf binary, so this particular function is invoked when you want to either load a binary data into a process or a shared library gets loaded into a particular process. So in the operating system, you would have a function like this, and importantly for us, there is a if condition present here where we check whether this randomize underscore va underscore space is greater than 1. So recollect that in the Linux systems, the randomize underscore va underscore space would take 3 values 0, 1 or 2. If the value is either 1 or 2, it would mean that ASLR is enabled on that particular system. So if ASLR is enabled on this system, we invoke this particular function arc underscore randomize underscore break, which essentially is present here. So what this function does is invokes this randomized range, which returns some particular random address. So this random address is then returned here, and at this random address is where the library is loaded. Thus we see how the operating system uses some random location in the process address space in order to load the library. Further on, during the time of loading, the loader would either fill the GOT table or go specifically to those particular locations and fill correct addresses in those global data. So in addition to the data, even the functions should be made relocatable. In the next lecture, we will see how functions are made relocatable. Thank you.